I'll start by giving a brief background of the work. So the first AIDS case in Uganda was reported from a fishing village in a place called Rakai in 1983. Since then, HIV prevalence and incidence has been high in the fishing communities of Lake Victoria relative to the general population and other high-risk groups. However, the transmission dynamics in these remote and hard-to-reach communities are still not well understood in Uganda. And understanding that these transmission dynamics is important for one to implement effective epidemic control in those communities. Because of the high HIV incidence rates in these fishing communities, they have been thought to act as reservoirs for viral transmission, and they have been characterized as a population that is driving the current epidemic in Uganda. Nonetheless, there hasn't been enough evidence to prove that indeed the fishing communities are a source of HIV transmission to the general population. We do know that phylogenetic techniques provide a powerful objective tool to examine viral transmission in populations. So in this first study, we sought to answer the question, are fishing communities of Lake Victoria sources of or sinks for HIV transmission from the general population? And our hypothesis was that these communities are actually viral reservoirs or sources of HIV transmission due to several reports of high HIV incidence.
Hi, can you FaceTime me real quick?
If I hold on a second. Yeah, okay.
Yeah, do it.
Okay, I'm doing it.
Are you doing it?
Yeah, I did it.
Can you do it? Yeah.
Is that? It's the lookalike of Debbie Newbold. You look great. How are you? You look great. It's a long time no see. Well, you're younger. You look...
Mike? Hello, Mike? Mike, could you mute your microphone, please?
Yeah. So the main objective in this first study was to identify HIV transmission networks in the fishing communities and general population, and at the same time reconstruct the temporal and geospatial viral transmission patterns in the two populations. So this was a cross-sectional study that was implemented in 8 fishing communities and 2 general population cohorts, where a total of 606 HIV partial pulse sequences from the fishing communities and general population were analyzed by phylogenetic methods. We also collected study participant social demographic data using structured questionnaires to inform this analysis. And we did identify HIV transmission networks by constructing phylogenetic trees and identifying those networks on those trees using the cluster picker program. So phylogeography was used to reconstruct the viral migration patterns between the two populations, the fishing communities and the general population. And we also performed a phylodynamic analysis in BEAST that was used to determine the temporal dynamics of HIV transmission in those networks. So this analysis comprised mainly of a BEAST analysis that we performed, where we implemented the Markov chain Monte Carlo algorithm for a chain length of 300 million generations sampling every 10,000th iteration. And we used a log-normal relaxed molecular clock with the SRD06 mode of nucleotide substitution and the SkyGrid trip prior. And these were determined as the optimum parameters for the data by the path sampling and stepping stone method. So the phylogeographic analysis was performed using an asymmetric discrete trait substitution model, and it was majorly based on the reconstruction of ancestral states and the count of the number of location changes that occurred in the phylogenies that were generated. Within the BEAST analysis, a Bayesian stochastic search variable selection method was used to limit the number of significant traits that adequately described the diffusion process, and also to generate a Bayes factor test that was used to assign some level of support for the transitions between the locations, between the different locations in the fishing communities and in the general population. And finally, the viral migration patterns were then reconstructed in another program called SPREAD. So I'll move on to the results. The phylogeography showed very strong support for viral migration from the general population to the fishing communities. And below is a table that shows the significant viral migrations with a Bayes factor of greater than 3 between the general population and the fishing communities. So we can see that actually obtained quite significant support for viral migrations, particularly from the general population to the fishing community. So this slide here shows two types of trees. One is generated in the program RAX-ML, and this is the tree that I talked about where we identified the transmission networks. And we can see here that the tree in the middle, we can see that actually some of the transmission pairs had really short branches where you would expect to have relatively low genetic distances. And over to the right, we have a maximum clade credibility tree generated from the B strands. And in this kind of tree, we can see that the branches are colored according to the locations. And at the same time, we do also have a time scale at the bottom. So those are different kinds of trees that we generated and analyzed in this analysis. So we also observed more recent HIV transmission pairs from the fishing communities at a genetic distance of less than 1.5% compared to the general population. And we can see in the contingency table showing pure subtypes pairs that were identified both at a genetic distance threshold of less than 1.5% and at a threshold of between 1.5% to 4.5%. We can see that at a genetic distance of less than 1.5%, we identified 10 transmission pairs in the fishing communities and 3 transmission pairs in the general population. While at a genetic threshold of between 1.5 to 4.5%, we identified 15 transmission pairs in the general population and only 3 transmission pairs in the fishing community. So this would suggest that most likely any linkage found among member fishing communities that you would identify in this analysis. And from the phylogenetic analysis in BEAST, we computed the mean time depth for pairs in the fishing communities and the general population. And we observed that the time depth was much shorter in the fishing communities at 5 months compared to 4 years in the general population. And the time depth here was defined as the difference between the time in years of the most recent sample or sequence in a pair or cluster and the most recent common ancestor, the common node. And this provided an approximation of the time when viral transmission took place. So the major finding for this first study was that there was really strong support for viral migration, as you can see in the figure above this slide, from the general population to the fishing communities, indicated by the arrow, by the black arrow. We did not find any substantial evidence of viral dissemination to the general population. And based on these findings, one would ask, what does this mean for interventions? And we thought that targeted interventions that have been advocated for a long time in the fishing communities should ideally be extended to include the neighboring general population for effective epidemic control. So these results from this study have been written up in a paper that was accepted by Scientific Reports late last year. So in the second study, we combine phylogenetics with modeling, and having established that the fishing communities are not sources of HIV transmission, but actually act as transmission sinks, we wondered what the underlying network structure in the fisher, particularly in the fisher folk community, is like. And if I can give a brief background, several transmission network studies have actually been done, and they're important in understanding HIV transmission in high-risk and general populations. Nonetheless, estimating parameters that influence network formation and evaluating the underlying network structure has not been done. And this is important in assessing determinants of disease spread or persistence in networks, that in turn is critical in predicting and making an informed decision about how to implement effective epidemic control. So we aim to estimate transmission network parameters and characterize the network structure from HIV nucleotide sequences, a total of 2017 partial pulse sequences from Lake Victoria fisherfolk communities, female sex workers, and the general population in Uganda, for the first time in these populations. And just to add a note, in the general population, we focused on cohorts that were sampled more densely. So this diagram is a summary of the methodology, and I'll quickly go through it. So we had HIV pulse sequences from the 3 Ugandan population, the fisherfolk communities, the female sex workers, and the general population. We identified transmission networks from RACSML-generated trees at a maximum genetic distance of 4.5% with a greater than 95% bootstrap support. We then refined those transmission networks using time-resolved phylogenies, where we included only those sequences that were estimated to have diverged less than 5 years before the most recent sampled sequence. And from there, we did generate network degree distributions, and then we fitted several models using the StatNet package in R to those distributions, and we are able to estimate parameters and describe the network structure. So results from that analysis, the degree distribution for all the sequences was approximated by power law, as shown by the graph on the left, but with an increase in the number of high degree nodes at increasing time depth from 1 to 5 years. As the time depth increased, the number of high degree nodes in the network increased with, as we can see from at 1 year, that is shown on the graph on the right, in blue, from 1 year to 1 to 3 years, and from 3 to 5 years. We see an increase in the number of nodes with high degrees as the time depth increases. And we also see an increase in cluster formation as the time depth increases. So we can say that the older nodes in the network had more connections or edges. You can see from this image here. I just wanted to portray that. So another finding from this analysis was that networks of Fisher-4 communities were scale-free with exponent gamma between 2 and 3, which suggested an infinite variance of the degree distribution. And this means that HIV transmission that might involve only a few but highly connected individuals in a network would actually result in a significant spread or persistence of the disease in a population if the gamma falls within this range of 2 and 3. So the graph below shows the distribution of bootstrap estimates for gamma with 95% confidence interval, shown by the red vertical lines, and the mean value for gamma for the exponent in the Fisher-4 communities was about 2.7. We can see on the graph on the right that shows the bootstrap resampling of other parameter estimates like the K-mean besides the gamma. So the gamma parameter is an estimation of the exponent for the power law distribution. So for the model results for the model fitting showed that the Waring, the Euler, and the negative binomial models fitted networks of Fisher-4 communities, the female sex workers, and the general population better, respectively. The Euler and Waring models are power law models that arise from a preferential attachment process. And this means that an individual who joins any network is most likely to link to nodes that have a higher number of connections as opposed to nodes with fewer links on the network. And the negative binomial model that fitted networks in the general population makes the assumption that individuals have a fixed rate of partner acquisition over time. So the major findings from the second study showed that the underlying network structure in the Fisher-4 communities was scale-free and shaped by preferential attachment in contrast to the general population. And I've already talked about the preferential attachment, where nodes prefer to attach to others with many connections. And the question here is that what does this mean for interventions? So we can say that this could suggest that probably while random interventions could be effective in preventing disease spread in the general population, the control of epidemics in high-risk population like the Fisher-4 communities would require early and focused interventions that are targeted at groups in the network with a high number of degrees. So these are individuals that are highly connected in such networks that would be targeted to this. That brings me to the end of my presentation. Thank you for listening. I would like to acknowledge Professor Pontiano Kalevu from the MRC UVRI, London School of Hygiene and Tropical Medicine, Uganda Research Unit. Dr. And I would also like to acknowledge Professor Andrew Lebra from the University of Edinburgh and Dr. Gonza Yebra. I would also like to acknowledge Dr. John Chitayimbwa from the UVRI Mui Plus, and Alfred Sekajay. Thank you so much.